RF section and got the exposure to phaco simulation tool. Today, I would like to request respected Dr. Kusum Lata ma'am of IIIT Allahabad to enlighten us on RF CMOS integrated circuits.
Very good morning to all of you. I hope all of you can hear me. I don't think I hear my mic right away. So in case if you're not able to hear, please raise your hand and we can interrupt you. So I'll be talking about RF CMOS integrated circuits. Now it is not very old that people started designing their RF circuits in CMOS technology. So it is somewhere around 90s people started talking about the RF circuits using CMOS. Right? So why people got interest into the CMOS technology and why people would like to design their RF circuits in CMOS today. Right? So all that I'll be talking. Next please. So this is the outline of my talk today. That introduction of the systems and the challenges and the design. That how people are designing and what are the challenges they are facing when they are designing their RF circuits using CMOS technology. Right? Then RF circuits and the MOS transistor scaling. That is where I'll be talking about why people got interest into the CMOS technology when they wanted to design the RF circuits. And then I'll be talking about the RF CMOS circuit techniques in nanoscale era and future prospects of the RF CMOS circuits, and after that I'll be summarizing. So this is what all of us we know, right? So I'll be just starting a few seconds only. So it is like when you talk about the wireless world, so there are a number of applications of it. Right? For example, you have laptops, you have TVs, printers, cell phones, camcorders, digital cameras, and then microphones. And then for having this connectivity, the wireless connectivity, there are a number of devices. For example, we have Wi-Fi, we have Bluetooth to connect all together. Right? Go to the next, please. Alright. So this is what we heard yesterday also. When we talk about the RF design, it is quite challenging, and because you need a multidisciplinary knowledge with you when you are actually going to design the RF. It could be a system, it could be a circuit, it could be a component, it could be a device. Right? So whenever you want to talk about the RF design, you need to have a multidisciplinary knowledge with you. For example, you need to know the communication theory, and when we are talking about the IC design, integrated circuit design, so we need to know how do we actually design the ICs. Right? And then we need to know the CAD tools, wireless standards, and we have different kind of multiple access techniques with us. Then signal propagation, micro. So there are like various fields we need to know when we are actually designing the RF circuits or systems. Right? Go to the next. This also have been discussed yesterday. That there are a number of trade-offs when we are designing actually the RF circuits or systems. Then we need to keep in mind this is known as kind of like RF hexagon. So these are the challenges, and there are a number of trade-offs between the two. Like for example, if you talk about non-linearity, linearity and the noise, right? So if suppose you want to have a system as a linear one, so then it is going to be a trade-off between the linearity and the noise. And similarly, you can see all the number of parameters, and they depend upon each other, right? So and whenever you pick one parameter, so another you have to pay off, right? So that is where you need to make a compromise for one with the another. Okay. So but in the today's era, that demand is for high performance, lower cost, and the greater functionality. So what people are doing is that when you are designing the ICs, you are putting more and more number of circuits, more and more number of components onto the same IC, and that is where we see like we would like to have as many functions as we want in a single IC. Right? So that is where we face the challenge that we would like to design the IC with the greatest functionality. Whatever we can think of, it should come in an IC. That is the challenge for the RF circuit designers. Right? So this is a typical example. Like for example, this is the direct conversion RF transceiver. So what we say is we have an antenna interface here from this left side onwards, and then you talk about the integrated circuits here. So this is a question where we will be talking about the integrated circuits. So typically when we talk about, for example, mixers here and then LNA and TLL, people used to design by using different kind of technologies, not CMOS. Right? So in 19 onwards, somewhere people started talking CMOS, because if you see this portion, that is digital basement circuits, right? So this is the one which people are actually already implementing using CMOS. So if you can design this portion also using CMOS, so what you can do is you can integrate all together onto a single chip, and that is where people start talking about, can we have a RF transceiver on a single IC? So that is where it motivated people towards the CMOS technology. Can we design our RF circuits or systems using CMOS technologies? Okay. Now, the advantage of CMOS circuits are, as we, the very interesting thing about CMOS is, as you scale down the transistor, we get FT. Okay, we get this FT. Okay, so this FT is inversely proportional to the channel length of the transistor. Okay, channel length of the transistor is your MOSFET, which is in here. So as we are scaling down these transistors, that is this. So this MOSFET we are scaling down, right? We are already somewhere around, we are talking about 40 nanometer, 22 nanometer, and people are expecting that you will be able to design by using CMOS somewhere around 11 nanometer, maybe after a few years from now, right? So that is what the target is. So as we are scaling down these transistors, the feature length of this particular transistor, so we are gaining here, and that is FT, and that is where it helps us a lot. That is this A, that is the gain of this particular circuit, that is which we see here, and this is your typical amplifier, right? So in this one we are gaining here when we are actually gaining in FT by scaling down the size of the transistors. Go to the next page. Yeah. Okay. So now in this one I'll be talking how people started designing the circuits using CMOS technologies. That is, I will talking for RF circuits. So people started talking about somewhere here, that is like 92 or 93, very first design came up with the CMOS technology. Now somewhere here, now when we were here, that is we were in micrometer technologies. Now at this point, FT is somewhere around 25 gigahertz and VDD is 3.0. So very first step was, people started talking about somewhere here in the 90s, and very first step was the components. They started designing RF components using CMOS technology. So when I say components, it is like the circuits which we will be talking, like for example receiver, and then we will be talking about the mixers, we will be talking about RNA, then we will talk about PLL. So all these components individually, they started thinking of like, okay, can we design these components using CMOS technologies? Okay. Now the next step came up somewhere here in the late 90s. Can we design a single transceiver? When you're using CMOS technology, can we integrate all together, and then can we have a single transceiver? Okay. Now in this one, that is in 2000, the people started thinking of, it is not yet has come, and it is not in the market, but people started thinking, and it is still in the research, that multi-mode and multi-band transceivers can be designed using CMOS technology. So somewhere here, they are still trying all that. Now the next step is, we will be designing the next generation RF circuits using CMOS technology. Okay. Now very interesting thing which you would see here, when we are talking about 45 nanometer technology, FT has reached to 200 gigahertz. And when you see your spectrum, that when you see the RF band, we have already crossed that. We are moving towards meter band, right? So we are already reaching towards that. So that is where it has taken the interest of the RF designers that we should be using CMOS technology. Now, if you go back, one slide. In this one more interesting thing was, the problem with this circuit is, if you would like to implement this using CMOS technology, the challenge is this, that we typically don't design this inductor using CMOS, right? Now this is the challenge. So now if you can somehow, you can compromise with this. Now since we are gaining here a lot, when you are scaling down with the CMOS, right, with the transistors, since you are gaining a lot here, so can you do something with this factor? That is what the research is going on. So if you can do with this one, and FT anyway you are gaining a lot, that is what we have seen into the next slide in this one. So that is where people started talking about the circuits using CMOS technologies. Okay, can we work only with the CMOS, right? And then at the same time we can gain the same performance of these circuits. Next page. Okay, so this is what very first time people designed that, and the references which I have taken here is this. For this particular talk, a number of references are there, and which I will be giving you at the end of this talk. So the one reference is this one. This is very first time in the 1993, they reported that the RF CMOS circuit, that is differential amplifier with a gain of 14 dB at the center frequency of 770 megahertz. And that is where people started thinking of, if we are able to achieve this much of center frequency and this much of gain, then can we design other circuits also using CMOS technology? Okay. Now, and at this time, our feature length was 2 micrometer. Now, today's we are talking about somewhere 45 nanometer, 22 nanometer, and we are targeting somewhere around 11 nanometer. So that was the time when it was having 2 micrometer feature length, and value of FT is thought to be around 1 gigahertz at that time. Now, since we were not able to compromise with the inductor, what can we do with this inductor? And that is where the challenge is for designing the RF circuits with the CMOS technology. Now, this inductor was indicated by using the Manch process in order to achieve the high self-resonance frequency and the high frequency. So these are the typical circuits. After the mid-90s, somewhere people started, they became like ambitious, can we design all the RF circuits using CMOS technology, right? So this is what they started designing. For example, this one is your LNA, that low noise amplifier using MOSFET, and this is your standard Gilbert cell, which typically we used to design using BZT, and people implemented this using MOSFET, and this is your cross-coupled DCO using MOSFET. So that is how people started thinking of, okay, can we change the topology with the MOSFET, and then we will be using the CMOS technology for designing the RF circuits. Okay. Now in the late 90s, somewhere we were there in 0.35 micrometer technology. Now in this case, the short range wireless LAN, that is Bluetooth, and this 2.5 gigahertz band, that can be easily implemented, was standardized. That is what people thought of, and they came very fast. They came very fast in the late 90s. They thought of, okay, when we can design this, and it was standardized also. The specifications were acceptable for the CMOS circuits, and the references given for this are these two. The integrated transceiver chip was introduced during this period, that is the late 90s, somewhere around 2001 and 2001. The second one also, they came up with the chip, that is the integrated transceiver we are able to implement with the CMOS. This is your typical one-chip transceiver that was introduced in 2001, and that's what I have already given. So this is just to show you that the Bluetooth one-chip transceiver using CMOS technology, how it has been implemented. So you see all the components have been integrated into a single chip. Okay. So as we are scaling down the CMOS technology, there is a number of problems which are coming out because of that. And now, as we are advancing the CMOS technology, we need to think of the new topologies of the circuits, and the challenges are we will be talking about here. Now, when the process technology is going down somewhere around 0.25, and then we are talking about this, and today we are talking about the nanometer technology. Now, the operation at this particular technology itself, that is 0.13 micrometer, we already reached to the point at FT at 5 gigahertz. It was already there. Right? Now, the R&D work for the transceivers for wireless LAN and then WCDMA GSM system, it was also initiated when we were working with this technology, that is 130 nanometer technology, and FT is here, this 5 gigahertz. Now the problems are when you are advancing the CMOS technology. When I say advancing, it is scaling down the MOSFET. Now the problem came up, like for example, when you are scaling down the technology, at the same time you are scaling down the VDD also, right? So the challenge comes up the low voltage operation. So whenever you want to design a circuit, it should be working with the low voltage. I'll cover all these in detail just after this. Then tolerance to the variations and the scalability in the RF circuits. Whatever circuit you design, that should be scalable with the CMOS technology. And then wideband operation. Yeah. One more interesting thing. Can you go back to my first slide? Maybe second or third. Hold on. Next one. Yeah, this one. Now, first. Yeah. This one, see, this is able to work in narrowband operation. has come already into the market using these CMOS technology. Now the power supply for this is 1 volt. Now the circuit which you are going to design, that you should be able to design with the power supply of 1 volt, and that is where the challenge is. Now the problem with this is it becomes very difficult to achieve the noise tolerance when you are working with this one, and a dynamic range using a low voltage power supply. And when you are especially talking about the cascaded transistors, you have the cascaded stacked transistors with you. For example, in Wilbur cell, you have a number of transistors sitting on top of each. Right? Yeah, go to next. This tolerance of variations. When we are scaling down the CMOS transistors, that time the variation in the transistor characteristics, this increases as the CMOS technology advances. When I say this, the variation in the transistor characteristic is when you are scaling down the MOSFET feature size and when you are actually fabricating that. So now when you characterize those transistors, so we see a variation between the functionality of one transistor and the another one. And that is where the challenge is with those, even it is a smaller one, but then also with those variations in the transistor characteristics, how do you actually design the RF CMOS circuits? Okay. Now the next is, it becomes very important to compensate for the increasing influence of the variations. Now, what we can do, we can advance our fabrication processing technologies by using which we are actually fabricating the MOSFET onto the silicon, and then power supply voltage and the temperature variations. All these have to be taken into account when we are designing our RF circuits using CMOS technology. Now, as we are going to design our RF circuits using CMOS, so we need to keep in mind that our circuit itself, the topology which you are actually borrowing, that should be scalable with the technology. Okay, that should be scalable with the CMOS technology. Now, the area occupied on the chip by the inductor itself is comparable with the area occupied by the transistors which are there on your IC. Now, the area occupied by the inductor, it cannot be reduced as the technology is advancing. When you are talking about the technology advancing, it means you are reducing the feature size of the transistor, right? But you are not actually reducing the size of the inductor. So that is where this is another challenge. Now, therefore, the fraction of the area of the SSD chip that is occupied by the RF circuits, that is including inductors, it increases, and thus the cost becomes very high. Okay. Next, please. This was another challenge that we have seen that it works in the narrow band operation. So now we need to see that how these circuits can work in the wide band operation. So expectations are the wide band RF circuits that enable multi-band, multi-mode operation, and it supports the several radio services. It would be developed, and that is what that has not come into the market, but that is what the expectations are, that RF circuit designer, they should be able to give you the multi-batch, multi-module operation, and it should also support the several radio services. So it is kind of like people are expecting, expectations are becoming kind of infinite. Whatever RF application you can think of, you would like to integrate all those applications onto a single IC. That is what people are expecting. Multi-band, multi-mode, and it should support the several radio services as well. Okay. Now, so with this, there has been a demand for an RF circuit that is capable of large signal digital processing. Now, when we are talking about your baseband processing, anyway it is already digital. So you would like to integrate your RF circuits with the digital baseband processing, and it can be used to support the multiple applications with the help of software programs or software control. That is the next again expectation. What people are asking is, for example, we would like to design these circuits, that is your SCR is your software defined radio, then you have your cognitive radio, recon field radios. All these systems also we would like to design all together, and for that we would like to use the techniques that is software programmable. Can we design IC having all the features in it, and can we make it programmable? So that is the expectation which people are actually expecting, that design a single IC and make it programmable. Okay, so that is what is challenging, and that is what people are still working on that, and they are hoping that we should be able to achieve this goal, that is SDR, CR, RRR, multi-band, multi-mode, and several radio services all together. We can design a single IC, and you can and make it programmable. So that is what the next goal is for the RF CMOS circuit designers. Now, after 2001, the studies aimed at solving these problems which we were talking about. For example, low voltage operation we talked about, wide band operation we talked about, scalability of the RF CMOS circuits we talked about. Now, in this one, single chip Bluetooth radio with all digital transmitter and a discrete time receiver. So what people did here is, earlier they used to talk about PLL, and that was kind of analog component in it. Now what they did is they replaced it with the ADPLL, and then they would like to have as much digital processing as we can have on the single IC. Okay. Now there are two methods for realizing a multi-band and multi-mode functions. So one can think of like integrating multiple transceivers on a chip. So what we started thinking of, the very first thought is that okay, design the different transceivers for each and every application, integrated all together on a single chip. So that was the very first thought which came up. So we can do this. Now next thought was realizing a programmable transceiver that can help you to control for carrying out the multiple application. Design a single chip, make it programmable, and you have software control, and your IC will work according to your requirement. So you will be programming it according to your requirement. So this is one thought that people would like to have the different transceivers sitting onto a single chip, and then you integrate it all. Now the job interface is you are going to have a choose area, and you are designing each and every transceiver, integrating it onto a chip. So you are going to while choosing onto the chips. Now next one is, this is digitally controllable software defined data SDR. So this is typically people started thinking of, you put all together here and make it programmable, and you should have a digital control with you, and then make it programmable so that it was for your requirement. Okay. Now the examples of the transceivers that were recently developed by the first method, that is your you have different transceivers sitting onto a chip. One chip transceiver that supports a WCDMA and 4-band GSM function, and as well as the transceiver that supports 2.4 and 5 GHz LAN along with SMA. So that is what it was reported that you can design something like this. Now the example of the transceiver developed by the second method is an SDR one chip transceiver, and it supports WCDMA, RTE, BiMAX, and your digital. Now this transceiver is based on your 40 nanometer technology, and it has been reported recently in 2010. All of these transistors are also equipped with a number of LNA. Then you have output amplifiers, RF signal modulation, demodulation, and PLL circuits are compressed for the number of applications. Now the expectations and the hope is, by adopting new transceiver architecture based on the advanced CMOS technology, versatile transceivers such as those used in SDR, CRR, and RR will be realized. That is what people are hoping. We are targeting that we should be able to achieve this goal with the new transceiver architectures, and that is going to be based on CMOS technology. Now here I will be talking about the RF CMOS circuit techniques in nanoscale era, where we are actually already designing. So there are different techniques. One is the design techniques based on the time domain control. Okay. Now in this category, we already talked about all digital PLL. So in the conventional PLL circuit, what used to happen is the output of an analog VCO is compared with the phase reference signal, and the result is fed back in order to control the oscillation frequency. So what you are doing is you are working into the analog domain. Now in this, when you are talking about all digital PLL, that is your ADPLL, these circuits, digital feedback control is there, and it is performed by using the DCO and the TDC, which we have seen in the previous slide. Next. So this is your typically digital controllable oscillator DCO. So earlier we were talking about VCO. Right? Now when we are talking about the CMOS technology, we started talking about digitally controllable. And in this, we are using MOSFET technology. And this is the cross-coupled oscillator. This is what we see with the RC resonate. But there are a number of small cellist vectors sitting over here. Now, for example, when I say number of, then digitally for frequency reading. That is the advantage of it, and because of that, we are able to fabricate it using CMOS. Now, this is the next component, that is time to digital converter. This is again the part of your ADVLL. Earlier, we used to talk about VCO, and then through that we are controlling. So what we did is we have separated it out with the VCO and then this TDC. The output signal is compared with the reference signal using this TDC. So the output of VCO is actually coming over here, and then you have a reference signal here. Right? So you compare it here, then the signal from the VCO is the input as to the delay line, which is here, that is the cascade inverter over here. Now by reading out the signal status at each tab, which is here, what you do is you generate the pseudo thermometer code as vector, and this is what again you use as a feedback to the VCO, and which you should be implementing by processing the code digital. Now this is another circuit, mixer, direct sampling circuit. Again in this one also we will start talking about, okay, we will be using this MOS transistor, this is MS here, and the carrier frequency for this we will be using this one. So now this circuit, if you see this particular one, you all over the place, you are using all these MOSFETs sitting over there. Go to the next slide, please. Now, the phase information of these modulated RF signal is stored in that capacitor CR, which is just next to your MOSFET sitting over there, and is given for the amount of the charge. Right? Now, information can be extracted by observing the change in the amount of stored charge, which you are actually storing into the capacitor over there. Go to the next please. Now, this kind of circuit, it offers the following advantage. For example, you have wideband operation, which can be achieved by changing the sampling frequency, which we are providing over there. And the circuit is suitable for the circuit integration because it is done digitally controllable circuit, and it does not have analog filters in it. Now, the one more component which we have here is RF signal generator based on the time to analog converter. It has the opposite functionality as you have as TDC. What it does is it generates the RF signal, and this has been implemented with the 90 nanometer CMOS okay. Now, another challenge was the scalable wide-band RF circuit. When we talk about scalable, it means the circuit performance should improve, and size of the circuit is decreasing as the technology is advancing when we are talking about the CMOS technology advancement. Now, in order to develop the scalable RF circuits that satisfy this requirement, this circuit is going to consist of inverters. That is where we will be talking about the number of transistors sitting in it. And when you are talking about scalable circuit with the technology advancement, it means people would like to use more and more inverters in it, so that it is reducing the size of your circuit, and at the same time it is giving you the performance. Now,